In this video, we're going to take a look at an important object, a very useful tool as far as these linear systems are concerned. And that object is called an augmented matrix, right? Now, to give you an idea of why this concept is important, I'm going to write down three linear systems, right? So I'm going to write three linear systems. Here's the first one. 2x minus y equals 4, and then x plus y equals 5. So that's one system. And here is the second system. 2x1 minus x2 is equal to 4, and x1 plus x2 is equal to 5. And here is the third system. 2a minus b is equal to 4, and a plus b is equal to 5. Now, if you were to look at these three systems and say, well, what do they have in common? How do they differ? Well, in the first system, I'm using x, y as my pair of variables. In the second system, I'm using x1, x2 as my pair of variables. And then in the third system, I'm using a, b as my pair of variables. So that's a clear difference. But what should be more important is that the coefficients are exactly the same. There's a 2, there's a -1, and then there's a constant of 4 here in the first equation. And that's true about this system as well as this system. And then the second equation, I have a coefficient of 1 in front of the x, a coefficient of 1 in front of the y, and then the b2, the constant in the second equation, is 5. And that's true about this second equation and also this second equation. So even though they each use a different set of variables, the coefficients are the same. And when you think about it, the solution set has to be the same for all of these. So in some sense, these are equivalent systems. I don't even need, they're equivalent in the sense that, so these are equivalent, and by that I mean they have the same solution set. And this version of equivalence is a little bit different than our previous version, which was based on the ability to change one system into a more convenient form using our elementary operations. Now we're saying, if all we do is just use a different set of variables, then we know for sure, as long as we keep all the coefficients the same, then we know for sure they'll also have the same solution set, right? And as we went through our elementary operations, it was a bit tedious having to keep track of not just the coefficients, but making sure that I have the x's and the y's, and if there were more variables involved, I had to keep track of all of those variables in addition to the coefficients. But what this little illustration should make you realize is that the variables are irrelevant, right? So the variables used, right, are irrelevant. So in fact, do we even need to keep track of the variables at all, right? If it's really just the coefficients that are important, right, then maybe we can find a more effective, a more efficient way of keeping track of all the relevant information, right? Okay, so keep that in mind. And what we're going to do is just, before I define what the augmented matrix is, I'm just going to define what a matrix is and then show how the augmented matrix allows us to be a lot more efficient in how we keep track of the information in our systems and equivalent systems, right? So I'm just going to give you a quick but correct definition of a matrix, just a little bit of notation, and then see how this new structure, this type of object, can be used to make our work with systems a lot easier. So a matrix is a rectangular array of entries, organized in rows and columns. Right, so that's going to be our definition of a matrix. So it's something that's rectangular, and then it will consist of entries, and it will be organized in rows and columns, right? So what I'm going to do is write down kind of a generic matrix just to show you what we mean. So here's our rectangle. Now I'm not going to draw an actual rectangle. I'm just going to use these big brackets, if you will, to indicate kind of the outline of the rectangle. Now, since the matrix is a thing, that thing needs a name. Typically, we name matrices by using uppercase letters, right? So it might be uppercase. Sometimes it might be uppercase and also written in bold. Obviously, I can't write in bold, but in most instances, uppercase. And once you see something like this, or there are some other ways that you can denote a matrix, you know that you're talking about a matrix, right? So this is the name. This gives me the rectangular structure. Now, what about the entries? Well, what I'm going to do, since my initial goal for defining a matrix is to help us with a linear system, I am going to use the same notation that we used for the coefficients of a linear system. So I'm going to use the A and the two subscripts, the double subscripts, 1, 1. So remember, we don't say this like A11. This is going to be read as A11. And in a second, we're going to interpret what that first subscript represents and what the second subscript represents in the context of rows and columns. So what I'm going to do is this. So the next one would be, not like that. So remember, in your first equation, these were the coefficients, and then you'd have like A13, and then I'm going to go across. And remember, just using the coefficients, assuming our system has n variables, we would go over to A1n, right? And then, so like the second equation, these would be the coefficients, right? Dot, 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 and then A2n, and then this pattern continues. Now the mth equation in our system would be AM1, and then AM2, and then AM3, dot, 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 AMN, right? And this is what we're going to call a matrix, right? So where are the rows? Well, rows go across, right? So for instance, this would be, so I'm going to use RI. This is going to be the notation for the ith row, right? And then CI will be the notation for the ith column, right? So row 1 would be the first row. So, you know, this would be row 1, this would be row 2, and then dot, 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 this would be row M. And then going across. Now going down, that's how we, that defines a column. So this would be the first column, second column, third column, dot, 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 and the nth column, right? So this array, this rectangular array, it has entries arranged in m rows and n columns, and we call this, the way we read this, we say that A is an m by n matrix, right? So when we're stating it something like this, like verbally, or writing it out symbolically like this, instead of actually denoting the entire matrix, we can just say, we always state the number of rows first, and then the number of columns, right? So that's good, right? So right here, so this kind of structure, and we can actually use the phrase data structure, because that's really what a matrix is. It's just a way of keeping track of lots of data. It's organized in rows and columns, and there's a structure in how we index those rows and columns. And yeah, so it's a useful data structure. It's actually super important in computer science, right? But that's not the focus of why we're using it. But as you can see, immediately this gives us a way of keeping track of all the coefficients in our system. So all the coefficients of the variables, we can keep track like this. And those are important, but these are not the only values in a linear system that are important. What about the b's, like the b1 and the b2 and the bm, right? What about all the constants that go on the right-hand side of our standard, linear system? So, but what we can do is we can essentially augment this kind of structure to add another column. And in this augmented form, it's understood that the very last column will represent the constants on the right-hand side of each equation, right? So an augmented, or let's say like this, the augmented matrix of and let's say standard m by n linear system is given by, right? Now, let me show you kind of another notation. So we know that A represents these entries arranged in rows and columns. So if I simply say, okay, take the A for the coefficients and then augment, which in this sense, augment is like you're adding to. So add another bit of information to the coefficients that are stored in A. You put a B there, and then you say, well, form a new array using these entries as well as the constants, right? So this is kind of the shorthand way, one convenient shorthand way of denoting an augmented matrix, with the understanding that the A's come from the coefficient matrix, if you will, right? And then these would be like just an additional column. So this is like a column of the BI's, or you could just say the constant on the constants from the right-hand side of the linear system, assuming it's written in standard form, right? But if we were to kind of expand it now, this is what it would look like, right? So I'm not going to write too many more entries, but here are the coefficients like that, right? Again, I'm leaving out a few of them, But just to give you a sense of taking what we have there, dot, 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 and then AM1, dot, 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 AMN. And then literally, sometimes you might see this notation there to really show the separation between the constants on the, or the coefficients on the left, and then the constants on the right. And you'll see this, your B2, and then dot, 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 BM. You might see it like that. Sometimes they might use a dotted line as the separator. Sometimes you won't see a separator at all, but then the question would have to convey somehow that you're working with a linear system, and this is its augmented system or augmented matrix, right? So this is simply just another way of keeping track of the information in a linear system without having to get bogged down in the variables, right? The variables are kind of stripped away, and they're really, as we noted above, they're irrelevant, right? It's similar like in calculus. If you have let's say you have a definite integral and your function is in terms of x and you're integrating with respect to x. If I just change all the x's to t's, it will still be the same definite integral. It would still have the same numerical value. You'd still have to use whatever technique in terms of x. You'd have to use the same integration technique in terms of y. So yeah, the use of the variables in as far as linear systems are concerned is also irrelevant. What's important are all these numbers, right? So that's good. So we have a new way of denoting linear systems. But what we have to then do is convert out those important operations from Gaussian elimination, right? We have to convert those operations, and we can't talk about equations anymore because technically speaking, we don't have an equation. There is no equal sign here. All we have is a collection of numbers arranged in this rectangular form. So instead of thinking of this operation, so what I'm going to do is write down. So this is our old way of denoting a swapping two equations in a linear system. What we have to do is write down what is the equivalent form now with this new structure that consists of rows and columns. Well, the thing about the augmented matrix is equation 1, or I should say equation I, corresponds to row I, right? So all I have to do is change my big E, and we're going to use the little r to represent a row. Which row? Well, we use a subscript to tell us that information, right? And then we still use the double arrow to indicate a swap, and then this would be now with row J. And now instead of saying an equation swap, this will be a row swap or row interchange, right? Now you might remember in a previous video, I kept using the word row because as soon as I see a linear system, my mind immediately goes to this, and I go to matrix mode. It's like Keanu Reeves or something. But I get in that matrix mode and I immediately start thinking of rows and columns, and that's just, it works. And once you get familiar and comfortable with linear algebra, you automatically start thinking about matrices and that structure, right? And then this conversion makes it easy to represent the other two operations. So remember the second one is where we took a non-zero constant, so okay, it can't be 0, and we simply multiplied one of our equations, right? Well, that gets transformed into simply, again, taking a non-zero constant, k, and multiplying now row I. So this would be, I'll just call this a times row. right? You're multiplying a row by a constant, a non-zero constant. And then finally, the one that really allows us to get that triangular form by eliminating certain terms, now the goal will be to eliminate certain entries. So we want to still get a nice triangular form, but now we're going to be just focused on entries and not necessarily, an x1 or a z or a y, right? So the third operation is when you take a constant times row I and then add that to, well, I'm still saying row, but equation I, and add that to equation j, and then that becomes the new equation j. And remember, the convention is this row is the row or equation that's being updated. So when I translate that, it will look like this. So this will be k times row I plus row j. And I sometimes refer to this, and some of the literature refers to this as like times row and then add, right? And these, on this side, these are called now elementary row operations, and they play the exact same role as these elementary operations in that it allows us to systematically eliminate certain terms in our augmented system, and then makes it easy, relatively easy, to solve via, say, back substitution, right? And in a subsequent video, we're going to do an example of just that. So I wanted to do one video where we introduce the notation, and then from here on out, we're pretty much going to be using this augmented form anytime we want to solve a linear system. So I know you can't wait to see how that works, and I'll see you in the next video.